The blue line is the classifier only. So we did some babysitting with the learning rate. So every like a set number of epochs, we reduce the learning rate. So as you can see here, so the x-axis the epoch, the y-axis the test accuracy. So as you go along, so here there's the drop in learning rate. So it first converges, drop in learning rate goes up, and then it went up here again, but then just converged here. Ours, you see, ours is very crazy because augmentation network is trying a lot of different augmentations, like crazy augmentations. It just goes crazy, 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 and then it goes up a bit when the learning rate decreases, it goes crazy, and then it starts converging. So, so it's very interesting. So the augmentation network, yeah. So if you see this kind of variations, like you know how to worry. Yeah. It's always a combination.
I have a question along the same.
Go ahead.
Yeah, were you saying something?
No, please go ahead with the question.
Okay. So yeah, I wanted to know if you did an analysis of the output values of the trained augmented network. So maybe you can take those average values after the forward pass on the whole data set and use those values as the transformation parameters with the standard networks. Yeah, so it won't be as good as yours because it won't be adaptive to each image, but it would be interesting to see how good it is compared to just using the usual transformations that we apply.
Okay, so you mean do the augmentations like manually and then take the average, like the average?
No, just train bi-level just bi-level end-to-end, and then just take the network and analyze the average, analyze the values that it gives for the transformation parameters. And we can take the average of those values and use those with, let's say, standard ResNet 50 on ImageNet and see how good that is as compared to the usual transformations that we apply.
So how do we do that? So I mean, it's very simple. So we take like any two objects in a pair, and we extract feature representations for those two images. So it could be either Gabor filter bank features, or it could be unit activations from different layers of a convolutional neural network. And then we compute the Euclidean distance between the two feature vectors. And that is our measure of distance between these two images in computer vision models.
Any specific reason to choose a Euclidean?
Not really. We actually tried different measures. We also tried the L1 norm. And I think I also tried using correlation distance.
And things like dynamic time warping doesn't work in this case?
I haven't tried that actually. But do you have any reason that it might change things?
Yeah, because Euclidean distance is again just comparing the two distances, right?
That's right.
I have
done
something Yes, I've done something similar for audio, and we chose dynamic time warping because it was taking the best distance possible. So accuracy was significantly improved when compared to Euclidean distance.
That's
because
right.
It was using that dynamic programming approach.
Yeah.
And we can also do the same thing with images, right? So I mentioned that we have these grasping images. What I've done here is I've extracted the hand and the object and then kind of just put random backgrounds from image data set in the background to blank out the green background that we had. And then what we can do is we can use a convolutional neural network to extract some features for each point in this image, right? And then we do this 3D aggregation. What that means is we use the pose of the object that we know, and we use the camera focal length and things like that, which is called camera intrinsics, to project these features. So you can imagine the 3D model of the object is kind of in this image, and you're projecting features from each of the pixel onto the 3D, onto the visible part of the 3D model, right? And then from various perspectives, you're doing the projection so that you cover the entire surface of the point cloud. And now that you have these features of the point cloud, then you can use the same point net to do the contact prediction.
Yeah, sure. Just for preconditioned steepest descent, so we usually, as I said, use it in convex optimization problems where we want to make the loss landscape or the optimization landscape much smoother, and thus help in making the optimization process much faster. So there's
landscape smoother. What does it relate to in practical terms when you say you want to make the landscape smoother?
So you mean like you can reduce the number of local minimas that you have. You can make the contour much smoother to traverse rather than having rough points where the gradient might be trapped and might not escape. So like
Understood.
it makes overall optimization much more smoother and easier. So I can like in like more mathematical terms is basically modifies the geometry of the objective function to increase the rate of convergence for gradient descent. So we know that gradient descent is essentially x k plus 1 step is equals to x k step minus eta k, which is the learning step, multiplied with the gradient or the nabla f of xk.
And this is go ahead, please go ahead.
Yeah, sorry. So in preconditioned gradient descent, we take a extra parameter called as hk, which is basically the symmetric positive definitive matrix, and we use that to modify our gradient descent steps so that the geometry of that objective function becomes much easier, and the rate of convergence essentially becomes much faster.